Welcome to Breadboarding. In the previous video we looked at the design of our NE555 LED flasher circuit, and we also looked at the schematic diagram that we developed for this. But before we start to wire up the breadboard, we need to first of all look at the capacitors and resistors and understand how to identify them and what are their different properties. So this is video number 3 in the How to Use Breadboards and Retro Digital Electronics series, and we're going to be looking at the resistors and capacitors. So let's take a look at the sorts of resistors that we're going to be dealing with. So I've got a number of cards here with resistors on. So this is all of the resistors going up in tens, starting at 10 ohms all the way up through 1 mega ohms and even 10 mega ohms. So we'll be looking at these under the digital microscope so you can see the change in the colour bands with the different values here. Then there's some general sort of values that we tend to use in a lot of digital electronics, so tend to be around LEDs and pull up and pull down resistors. And then these are just some various other sizes of resistors, starting with the very small ones, which are about 1/8 of a watt, going all the way up to this big power one here, which is 10 watts, 10 ohms. If we were to put 10 ohms across a USB 5-volt power supply, then it will generally draw about 2.5 watts. So that will be about half an amp. And when I was testing out the various adapters in some of the earlier series, I used multiple of these in parallel to try and load up the USB power supplies. Let's just have a quick look at the color coding first. So resistors are used to limit current, divide voltages, and when you hear about RC time constants, so the R is in this is the resistor, so resistor and capacitor, and that's how we can change the timings of clocks and delays and things like that. We also use resistors for pulling up I/O lines. It's measured in ohms, and quite often we refer to it in K and M or meg. We don't often use milli when we're talking about resistance. Milliohm resistors are really only used probably in measuring current in ammeters and things. You'll probably know from school your Ohm's law, V equals IR, and that's probably about as much maths as you really need to know for dealing with digital electronics. There's a good tutorial at SparkFun, so SparkFun have a number of really good tutorials. I'm not going to try and reproduce those just because they've probably done it much better than I've done. But what you can see over here is, I think this is from Wikipedia, that the colour coding on resistors, most resistors are going to have 4 bands. They tend to have a tolerance band on one end, so 5% tolerance is normally gold, and that's what most of the ones you'll ever use will be. You don't really need anything much higher tolerance than that generally. And you get 3 bands. The first 2 give the value, and the third one gives the number of decimal places, or a number of tens really. So in this particular case we've got blue, which is 6, grey, which is 8, and then we've got a 2 here, and that basically means 10 to the power of 2, so it's 100. So what we've actually got is 6, 8 and 100, and that works out to be 6.8 kilo ohms. Now there are a higher number of bands, so in particular there's one resistor I'll show you to do with the VGA output where we need a 75 ohm resistor, and in this case you actually have a higher number of bands, and in fact the tolerance in that case will be 1%, which is brown, and then we end up with 4 values for which the 4th band there is actually the number of zeros. And again we'll come back once we've looked at the 75 ohm resistors. There's actually an extra bit we need to know about here anyway. So generally this sort of from 0 all the way up to 9, you tend to get to know probably the lower ones better than the higher ones. We don't often use 8s and 9s, to be honest. Very rarely that you'll ever see white and grey bands on most resistors you use in digital electronics. So I'll go back and have a look at the colour bands now, just so we can go through the various values. So we've got a number of resistors here, variable resistors on the left, and we're going to be looking first of all at the tens power series. So these are all multiples of 10. They start with brown black, and then the other colour then determines how many zeros are on the end there. So starting at black for 10 ohms and going all the way down there to blue for 10 mega ohms there. So let's take a look at these under the microscope. Okay, so the first one there, what we've got there is brown, black, black. That means that the 10 is in fact 0, so 10 to the power of 0 is 1. So in fact, that just gives us 10 ohms. But the way how these bands show, we can only go down. This is the lowest value you can do with the black value there. And when I come back to the slide later, we'll have a look at how we can do values less than 10 ohms. Then we're going to brown, where we've got 100 ohms. Red, 1K. So you'll quite often get to know some of these color combinations. So brown, black, red is a very common one that you'll be dealing with. And similarly, brown, black, orange for 10K is another very common one. Then less common will be some of these other ones. So 100K, got yellow there. 1 mega ohm is green. And then should you ever use it, then 10 mega ohms in fact blue. It's not terribly easy to see that, but that's actually blue. So when we look at all the other values, obviously the first two colors may vary, but the number of 10s, or the power of the 10, is the third band generally, and that's what we're looking at there. And then we've got another one here, which is the various common values. So for example, 150 ohms and 220 ohms are quite often used for LEDs. And you'll see there that what we've got there is brown, green, brown. Then for 220 ohms, we've got red, red, brown. And a little later on, we'll look at the 110 higher than that, so the 2.2 kilo ohms. In a minute, 330, which is the one we were using earlier, which is orange, orange, brown. So brown basically means 10 in the normal scheme of things. Then 560 ohms is green, blue, brown. This is what I'm talking about. So red, red, red is 2,200 ohms, or 2.2K. The pull-up resistors using digital electronics are quite often 4.7K, and this is actually yellow, sort of violet, then red. So the difference between the blue and the violet isn't terribly clear here, but this is actually a violet one. Then 5.6K is also sometimes used for a pull-up resistor, and that's where we got green, blue, red. Then finally, this other load has just got comparison of the different sizes. This one at the top is actually an 1/8 of a watt. It's a very, very small one. And even with the microscope here, it's actually quite difficult to see. But you can see here that this is actually a 75 ohm, 1% tolerance resistor. And you can see there we've actually got 5 bands. So the right-hand band there is in fact brown, which means it's 1% tolerance. And the fourth band there you can see is gold. Now what that means is it's 0.1 of 10. So it effectively means divide the value by 10 effectively. And so you can see here that we've got violet, green, then black. That makes that 750. But then because we've got this gold band, then that multiplies it by 0.1. So that brings it down to 75. And then we've got a 0.25 watt 75 ohm resistor there as well. Then going up, we've then got half watt resistors. So generally we're not going to need to use half watt resistors. In more analog and audio things, you may need to use higher resistor values, but generally the half watt you're probably not going to need. The only good thing I could say about the half watt resistors is that the leads tend to be a bit thicker. Some of the quarter watt resistors, the leads can be quite thin. Certainly on cheaper breadboards, sometimes you may have trouble with connections. Then finally, I think this one here is a slightly higher one, probably about 1 watt, about 2K. And then finally down the bottom here, this is another thing that you'll see quite often on digital circuits. So where you need a lot of pull-up resistors, say for the bus rails, so like the data bus or the address bus, then this resistor array has 9 pins on it. And what you'll see is the pin on the end here has got a little dot, and that means that's the common. Then all these ones are actually got their own independent resistor going to this common rail. So if we tied this to 5 volts, then it would pull all of these, would then be pulled up to 5 volts, or we could pull them down to ground if we wanted them pulled down to ground. So that resistor array is quite handy, certainly in breadboards. You don't have to have lots and lots of individual resistors being plugged in. So now if we clear these away, and we'll have a look at our variable resistors, potentiometers as they're also known as. So this first one here is more of a slider one, which tends to be used in more analog amplifiers and things like that. This particular one happens to be logarithmic. Most of the variable resistors we're interested in will have a linear scale, but logarithmic is more needed for audio. This trimmer here, these particular ones have quite nice thin pins that will plug into breadboards. This is an older one I've got that's been soldered in, and they're quite a bit thicker, so they would need to go on a little adapter. And this one down the bottom is actually manually it's got a knob on it, so rather than needing a screwdriver, we can just use our fingers to turn that, so I'll be using that later. And this one below is a 10-turn variable resistor, so this is able to be adjusted a lot more finely. So you see the little screw on the top there, you put a small screwdriver in there and you can turn it up to 10 times. So it allows you to be able to make changes a lot more accurately than the ones above there, which tend to be a bit crude. And this particular one is also being used for varying the constant current source that we needed for the VGA video output, the digital analog converter. So those ones are quite handy. One of the things I always wondered about resistors is why we have the certain values that we see. And in fact, it's down to the various tolerance. So with a 5% tolerance, there are a range of values that there's no point in having all of your values going all the way up to, up here, varying by 0.1 of an ohm, because in fact, with 5% tolerance, there's actually going to be an overlap between the different values. And in fact, what you'll see is that the E24 series here and the E6 series in green is the 20% tolerance. And quite often when you get resistor packs, the ones I've got, for example, will have 1, 1.5, 2.2, 3.3, 4.7, 5.6, 6.8. Sometimes they might also have the 8.2 as well. But in general, you'll find that most of the time you'll only need these sort of values in this sort of range. And there is a Wikipedia article on this E preferred ranges. When you come down here, it shows you all the different values that, depending on the tolerance, then you'll actually have the varying values. So that's where I've got these from. I'll include the links in the description below. When we're using a 1/4 watt resistor, then in fact, if we put a 1/4 watt resistor across 5 volts, in fact, we should only put up to 100 ohms there. Anything less than 100 ohms across 5 volts, and we would actually potentially cook the resistor, and it might actually get very hot and could even degrade. And the values that we're going to be using for resistors, generally LEDs, as we showed in the previous video, will be between about 150 ohms up to perhaps 1 kilo ohm. Pull-up resistors can be 470 ohms up to about 10k, depending on the technology we're using. Pull-down resistors, so if you need to pull down an input to 0 volts, that tends to need to be a little bit lower value. And this other one, the VGA video red, green, blue output, needs to have 75 ohm resistors, and that's where we get these 1% resistors, and that's at a voltage of about 0.7 volts. And also, you'll also notice that 1.5 ohms is quite often written as 1R5, and you'll see these other values. And also when we get to 1.5 mega ohms, you might write it as 1M5. So if you see this nomenclature, then that's just another way of writing this. Putting ohm characters in everywhere is quite awkward, since it's not a particularly easy character to insert into most applications. So when we were looking at the 75 ohm resistor, we saw that there was a gold band that meant 0.1 for the power of 10. And in fact, this diagram comes from the SparkFun tutorials. In fact, this diagram is probably a bit better than the one I showed on the previous page, but it didn't quite fit. So what I've shown here, we've got our 75 ohm 1% resistor. And if you remember, the values we had there were 750, gold, then brown. So if you just take you through what those values are. So we have the 4-band, 5-band, and there's also 6-band here, though I must admit I haven't seen many of these. The 6-band ones also include a temperature coefficient, so how does the value vary by temperature, which is not really going to be a problem for the sort of circuits we're doing. So if you look at our 5-band values, so we've got violet, green, black, so that's 750, 750, but then we've got gold, that means the multiplier is 0.1 or divide by 10. And then we've also got our 1% tolerance here. So in fact, the value here we need to know about this gold multiplier and also silver. So if we're dealing with very small resistance values, for example, we're dealing with less than 10 ohms, then we would need the gold and the silver values to actually identify the lower values of resistance. So now we're going to take a look at the capacitors. So here's some example capacitors, starting at a really big power supply one. So this is 45,000 microfarads, and this was the capacitor I used on my original nanocomp back in 1981 and was used to smooth the 5-volt power supply. Then we've got varying sizes of electrolytic capacitors, a tantalum one, and then various lower value ceramic ones. So we'll just go and have a quick look about the capacitors first, and we'll go and have a look at how to read some of the values under the microscope. So capacitors are passive components, and they're used really for storing charge, a bit like a small battery, I guess you could think of it really, and is mainly used for power smoothing, and also when we talk about RC time constants in delays and frequencies, then C is capacitance in that. So it is measured in units of farad, but a farad is extremely large really, so we tend to mainly use microfarads, nanofarads, and picofarads. So a picofarad, if you look over here, is 10 to the minus 12. So capacitance generally is a much smaller measure. These other measures, kilofarads, would only be if we were using supercapacitors, which are more like sort of large batteries. Millifarad, I don't think I've ever seen anyone use that term, but we normally use microfarad, and even if we're talking about 45,000 microfarads, we tend to use the microfarads in preference to 45 millifarads. And most of the capacitors we'll be using will probably be a few which are about 10 or 20 microfarads, and most of the other ones are 0.1 microfarads, and then a lot of them, the smaller ones, are used for things like crystal oscillator timing, and certain smaller values are also used for interfacing things like PS2 keyboards and stuff like that. The unpolarized ones are ceramic, are generally used for these oscillator timing. Ground bounce, talk more about what ground bounce is, but you'll see that in most of the designs we put 0.1 microfarad capacitors fairly close to the power input pins on the chips, and that basically stops interference on the power rails from causing data corruptions and things like that. One of the things which is a bit confusing, certainly when we look at the smaller values, is that quite often in the small values, everything is assumed to be a picofarad unless you have something else to tell you otherwise. So if you see a value of 2.2, that's 2.2 picofarads. If you see 221, then that effectively tells you that the one that we've got a 0 in there, and in fact in this particular case 102 actually means 1,000 picofarads. So the 1 0 and then another 2 zeros on the end there. So 1,000 picofarads is 1 nanofarad. It's quite important that the electrolytic and tantalum capacitors are polarized. That means there's a plus and minus, and it's very important to get them the right way around. Tantalum capacitors in particular, if you put them in the wrong way around, they will blow up and you'll see smoke coming out of them. And what I tend to do, as we show you, is put a black mark on the cathode or the negative side of things on the body, because they tend to be quite difficult to see. There's also a good tutorial on SparkFun. So SparkFun has a lot of the information that I'm sharing with you. Also shows what the symbols are. So in general, the unpolarized ceramic type capacitors tend to have the two plates like that, whereas the polarized ones will tend to have that shape with a plus on one side. And this goes into how they are actually made. And we don't really need to worry too much about the equations and all of the maths behind it, because generally, as long as we've already calculated what our value would be, then we don't need to worry too much about that, particularly in digital electronics. We're normally using most of the capacitors for power supply smoothing. And this is what a capacitor will do. It will smooth out the voltage. So I'll include those links in the description below. So we've already looked at the large 45,000 microfarad one. I'd say these days modern power supplies are used switch mode power supplies. They don't tend to need such large capacitors. This one's probably one of the larger ones you probably see these days, 10,000 microfarads, and then 2,200, 1,000, And then this is more like the ones you'll probably see in most of the breadboards. So generally we might include perhaps a 22 microfarad or 10 microfarad capacitor. In our 555 circuit, we're going to be using a 1 microfarad capacitor for the C part of our RC delays, the timing there. And the tantalum, you can't easily see what the markings are on here. Most of the markings on here are fairly straightforward. If I take one of these into the microscope, you can see here we've got the 1 microfarad, and if you'll also see on there, they generally will have quite clear, the negative or cathode side will quite often have a white stripe, so that's how you can tell which side you need to plug into ground. And the tantalum ones is a bit more difficult to see. You'll see there that it's basically saying 226. That probably means it's 22 million picofarads. So that means it's a 22 microfarad. And I think that says that it's 10 volts. And the plus side is on the long pin there. And what I tend to do when I'm using these, I tend to put a black marker on the negative side, so I put them in correctly. When you plug these in the wrong way around and turn the power on, you'll hear a crack and smoke will come out of them. Then when we look at these other values, you can see that the 2.2 picofarad just has 2.2, 4.7 picofarad, 4.7, then 22. This is quite often one that's quite often used for crystal oscillators. And then the 100 picofarad has got this 101, means 10 then with another 0 on the end. 150, you can read that on the writing on the capacitor itself, it's 151, which means it's 150 picofarads. And then when we go down to these other ones, then this is showing, so we've got 1 nanofarad, which happens to be 1000 picofarads, or has 10 then a 2, so that effectively means 10 followed by 2 zeros gives us 1000 picofarads. And this next one here, slightly different design, but the same sort of thing, is 0.01 of a microfarad, 10 nanofarads, and 103. So that effectively means that would be 10,000 picofarads. The next one along, this is the most common value we use in most of the breadboard circuits, 0.1 microfarads, 100 nanofarads, and a 104, and that is the one that we use most of the time. And then one of the higher values of the ceramics here is 1000 nanofarads, 1 microfarad, 105 you'd see on that. Now, I would say that it's quite difficult to read the values on here quite often, even with a microscope, but quite often if you get your capacitors sort of from various suppliers, so Bitsbox actually put them in a nice little packaging and actually include the 102 on there as well, so you know when you've got a 1 nanofarad 1000 PF, then in fact it has a 102 on it as well, which is what we have down the end. So if you do get them all mixed up, it is possible to work out what the values are, but generally it's a lot easier to keep them in the packets, and then you don't have this problem. So I thought I'd do a little experiment. So what I've got here is the 10 ohm 10 watt resistor plugged into the breadboard here. You can see it's been running now for a couple of minutes, so the actual resistor's got quite warm, so this should be about 2.5 watts. So it's well within the 10 watt rating for the resistor, but it's still, hot to touch. And you can see it's got 5 volts there, and the ammeter is showing just under 0.5 of an amp. That work out that power is volts times amps, that will be just under about 2.5 watts. So what happens if we actually put smaller resistors in here? So to start with, I'm going to try a 100 ohm resistor. So this 100 ohm resistor, this theoretically is a 1/4 watt resistor, and so this should be about a 1/4 of what this resistor will be doing. And then we'll also try a 10 ohm resistor. So this one should probably die somehow, so we'll see exactly how. And I've got the digital microscope set up here as well, so I'll put that to focus on it so we can actually see what happens to it when we turn on the current. I'm just going to put in the 100 ohm resistor first of all. So we'd expect this should be okay. It might get a little bit warm, but we wouldn't expect it to come to any harm. Just take this out, it's quite warm. Put it there for the moment. Now just wire in this. I'm just going to turn the power on. And we can see here on the meter there's about 51 milliamps. So just zoom in and have a look at the resistor. So it's been running for a little while. The temperature is warm but not bad. So that's as expected. But now we've swapped out the 100 ohm resistor and now I've turned on the power. It will take a little while for it to warm up, but you'll start to see that the gold paint will start to blister and then it will start to darken and you'll see some smoke and it starts to smell quite bad. Now when I took this out afterwards, it did still measure 10 ohms, so it hadn't actually been destroyed at this point. So you can see there that if we put two lower resistance across 5 volts, then obviously over time it will not do it any good. Take this, it does smell quite bad. I'll leave that there for the moment. So, tantalum capacitor, you can see that the black mark there is the cathode, so the negative side, and there's a very small plus, in fact, on the other side of it. So to start with, I'm going to plug it in the right way around, so we wouldn't expect anything very exciting to happen with that. Power is switched off. Okay, in the right way around, then nothing very exciting happens at all, so now we'll swap it around to the other way around. Initially I set this as 1 amp and then I later changed the power supply to be able to do up to 3 amps. So we'll see that after that change has been done, it starts to discolour and then starts to leak. The little spurt there and then you get smoke coming out of it. This doesn't actually catch fire, this one, but what we'll do in a minute is we'll rerun this with 4 amps and see if that is any different. The reason why it didn't start smoking earlier is because I had the bench supply set to 1 amp. When I changed current to 3 amps, then that's obviously what caused it to start smoking and to crack. So now rerunning it with 4 amps, and when I was doing the breadboard PC, the power supply was set at about 4.5 amps. So that's why I probably saw them explode. You'll see the colour start to change, it starts to spew smoke, and then it will actually kind of crack and catch fire. You now see it sort of catching fire, and in fact it all turns black. So I turned off the power at this sort of stage because I didn't really want any more smoke or fire, but it certainly makes quite a noise when it actually goes pop. So that's what happens when you take a tantalum capacitor, put it the wrong way around, and if your power supply is able to deliver enough current, so this is set at 4 amps, then that's what happens. It catches fire and generates lots of fairly unpleasant smoke. So in the next video, what we're going to be doing is looking at wiring up the 555 LED flasher circuit. So if you don't want to miss out on future videos, then please hit subscribe, and if you can hit like as well, it just helps to make the videos available to more people. Thanks for watching.